What if the object we've been tracking through our solar system isn't coming alone? What if 3i Atlas, the interstellar visitor that has captivated astronomers for months, is fragmenting into something we've never witnessed before, a swarm of debris that's now bearing down on Mars with implications we're only beginning to comprehend? Tonight, we venture into a realm where the reassuring predictability of celestial mechanics crumbles, and the unsettling reality of multiplying objects in our cosmic backyard takes root. For weeks, telescopes around the world have been trained on 3i Atlas, charting its unprecedented journey through our solar system. Initially classified as a simple interstellar comet, this visitor from beyond carried with it the promise of scientific discovery, a pristine sample of material from another star system, a cosmic messenger bearing clues about the formation of worlds light years away. But something has changed, something fundamental. The observations coming in from observatories across the globe tell a story that no one anticipated, a narrative that transforms this scientific opportunity into something far more complex and perhaps far more concerning. The data is unambiguous even if its interpretation remains maddeningly uncertain. Where once there was a single object, a solitary traveler making its way past the Sun, there are now multiple signatures, dozens of them. The fragmentation event, if that's truly what we're witnessing, began approximately 3 weeks ago as 3i Atlas rounded the Sun and began its outward journey. At first, astronomers attributed the brightening and expanding coma to typical cometary outgassing, the sublimation of ices exposed to solar radiation, a process we've observed countless times. But the pattern didn't match the secondary objects. These fragments or companions, or whatever they truly are, don't behave like typical cometary debris. They're maintaining velocities that shouldn't be possible for passive fragments. They're following trajectories that seem almost coordinated, though that word carries implications that stretch the boundaries of conventional explanation. And now this swarm, because that's what it's becoming, isn't it, is on a collision course with Mars. Not a direct impact, the calculations show, but a close approach that will bring these objects within the orbital space of our neighboring planet. Mars, with its thin atmosphere and vulnerable surface infrastructure, with our rovers and orbiters and the accumulated investments of decades of exploration, sits directly in the path of this expanding cloud of interstellar material. The closest approach is projected for 47 days from now, give or take the uncertainties that plague these calculations when dealing with objects that refuse to behave as predicted. The question that haunts the quiet hours in observatories, in the offices of space agencies, in the minds of anyone who understands what we're seeing, is simple and terrifying in its implications. What happens when dozens of objects, each potentially kilometers in size, each carrying velocities measured in tens of thousands of kilometers per hour, each originating from a star system we can barely fathom, passes through the Martian orbital space? And more fundamentally, more disturbingly, why are they multiplying? What mechanism could account for a fragmentation event that continues, that proliferates, that seems to generate new objects at a rate that defies our models of how comets disintegrate? Tonight we're going to explore every angle of this developing situation. We'll ground ourselves in the facts, in the hard data that forms the foundation of scientific understanding, but we'll also venture into speculative territory, because there are aspects of this phenomenon that demand we consider possibilities beyond the comfortable boundaries of conventional explanation. We'll examine what the authorities are telling us, what the numbers reveal, what the worst-case scenarios look like, and what it all might mean for our understanding of our place in a cosmos that seems determined to remind us how little we truly comprehend. Before we dive deeper into this unprecedented story, if you're intrigued by cosmic mysteries and the very real challenges of tracking objects that venture in from interstellar space, make sure to hit that subscribe button and ring the notification bell. Drop a comment below telling me what time it is where you're watching from and where you're located. I love seeing our global community come together to explore these cosmic questions that unite us all under the same stars. And if you appreciate the research that goes into these deep dives, a like really helps the channel grow and allows me to continue bringing you the latest developments as this situation unfolds. Now let's continue our journey into the mystery of 3I Atlas and its multiplying companions. Let's address the question that's undoubtedly foremost in many minds. Is 3I Atlas, along with its growing collection of companion objects, a threat to Earth, to Mars, or to our exploration assets in space? The official position from NASA, ESA, the International Astronomical Union, and every credible space agency that has weighed in on this matter is unequivocal. Number 3I Atlas poses no threat to Earth. The trajectory calculations, which have been refined continuously since the object's discovery 8 months ago, show that the closest approach to our planet occurred weeks ago, when the object was still a unified body, and even then it passed at a distance of 0.7 astronomical units, roughly 105 million kilometers away. The Minor Planet Center, which serves as the clearinghouse for observations of small bodies in our solar system, has issued 3 separate trajectory updates in the past month. Each refinement, incorporating thousands of additional observations from professional and amateur astronomers worldwide, has confirmed the same basic conclusion: Earth is not in danger. Dr. Sarah Chen, the lead astronomer coordinating the International Observation Campaign, stated in last week's press briefing that the probability of any fragment of 3I Atlas intersecting Earth's orbit is less than 1 in 10 million, and that's being extremely conservative with our error margins. But Mars is different. Mars sits squarely in the path of the expanding debris field. The calculations show that the closest fragments will pass within 50,000 kilometers of the Martian surface, a distance that sounds reassuring, until you remember that our most valuable assets in Martian orbit, including the Mars Reconnaissance Orbiter, the MAVEN atmospheric probe, and the European Space Agency's TRACE gas orbiter, all operate in orbits that extend beyond that distance. The Martian orbital space, that region where our machinery circles the red planet, conducting science and relaying data from surface rovers, overlaps with the projected trajectory of at least 17 distinct fragments. NASA's Jet Propulsion Laboratory has been transparent about this concern. They've initiated precautionary measures, calculating maneuvers that could move our orbital assets into safer positions during the closest approach window. These aren't panic measures. They're the same kind of prudent adjustments that mission controllers routinely perform to avoid space debris or optimize scientific observations. The Perseverance rover, safely on the Martian surface, faces minimal risk. The thin Martian atmosphere, while insufficient to burn up large fragments, will cause smaller debris to decelerate and disintegrate long before reaching ground level. The reassurances are grounded in solid orbital mechanics. Space is vast. Even a close approach in astronomical terms involves distances that dwarf human scales of reference. The probability of any single fragment actually colliding with any of our Martian assets hovers around 1 in several thousand. Not impossible, but unlikely enough that mission planners aren't losing sleep. These are objects measured in meters to perhaps a few kilometers, scattered across a volume of space measured in hundreds of thousands of cubic kilometers. The odds favor us. Yet there's an undercurrent of uncertainty in these reassurances that's worth acknowledging. The fragmentation behavior of 3I Atlas doesn't match standard cometry models. New fragments continue to appear in observations, each requiring updated trajectory calculations. The predictive models work beautifully for objects that behave as expected, following the laws of physics we've tested and verified countless times. But when an object refuses to conform to expectations, when new variables emerge faster than our models can incorporate them, the confidence intervals widen. The safety margins shrink. Despite these reassuring facts, despite the careful calculations and the transparent communication from space agencies, what shadows might lurk in the gaps between our observations? What assumptions underlie our confidence And how robust are those assumptions when confronted with a phenomenon that continues to surprise us? The question isn't whether 3i Atlas threatens us today. The answer to that is clearly no. The question is whether we truly understand what we're seeing and whether our models account for all the variables at play in this unprecedented situation. The statistics surrounding 3i Atlas and its fragmentary swarm represent extremes that challenge human intuition. Let's ground ourselves in the numbers because they tell a story that's both reassuring and unsettling in equal measure. Understanding the scale of what we're observing requires more than just reciting figures. It demands context, comparison, and an honest acknowledgement of the uncertainties that still plague our measurements. The parent object, 3i Atlas, as originally catalogued, measured approximately 4.2 kilometers in diameter. To put that in perspective, imagine 14 Empire State Buildings stacked end to end. This wasn't a small rock tumbling through space. This was a mountain, a floating peak of ice and rock that has traveled for potentially millions of years to arrive in our solar system. The initial velocity measurements taken when the object was first detected beyond Jupiter's orbit showed it moving at 34.7 kilometers per second relative to the Sun. That's 124,920 kilometers per hour. A rifle bullet, for comparison, travels at roughly 1,000 meters per second. 3i Atlas was moving 35 times faster. The fragmentation event, which current estimates place at approximately 23 days ago, occurred as the object was 1.4 astronomical units from the Sun, about 210 million kilometers, or roughly the orbital distance of Mars. The timing coincides with a dramatic increase in cometary activity, suggesting that solar heating played a role in the breakup. But here's where the numbers become truly staggering. The fragments are separating from each other at relative velocities between 50 and 200 meters per second. That's not typical for passive fragmentation, where pieces should drift apart at speeds measured in single-digit meters per second. Current tracking efforts have catalogued 43 distinct objects in the debris field. That number was 37 just 4 days ago. Either we're detecting fragments that were previously too small to resolve, or, and this is the possibility that keeps astronomers checking their instruments, new fragmentation events are occurring continuously. The largest confirmed fragment, designated 3i Atlas b, measures approximately 2.1 kilometers in diameter. The smallest, reliably tracked fragments hover around 100 meters, though there's undoubtedly a population of smaller debris that remains below our detection threshold. The total mass of the system, calculated from brightness measurements and assumptions about albedo reflectivity, is estimated at 8.2 × 10^13 kilograms. That's 82 trillion kilograms. To offer a relatable comparison, that's roughly equivalent to the mass of Mount Everest. We're watching a mountain chain, disassembled and scattered, hurtling through space at speeds that would carry it from New York to Los Angeles in less than 2 minutes. The kinetic energy contained in this system is almost incomprehensible, approximately 4.9 × 10^22 joules, or roughly 12,000 times the energy of the largest nuclear weapon ever detonated. The projected closest approach to Mars, as of the most recent trajectory update, will occur in 47 days, with the debris field passing within 50,000 to 180,000 kilometers of the Martian surface. The uncertainty range in these predictions has actually increased over the past week as new fragments appear and trajectories are recalculated. The fastest-moving fragments will traverse the Martian orbital space in approximately 6 hours. During that window, anything in their path faces potential danger, though again, the vast emptiness of space works in our favor. Historical comparisons offer some context but limited comfort. We've observed interstellar objects before, one Oumuamua in 2017 and 2i Borisov in 2019. Oumuamua remained intact throughout its passage, while Borisov showed typical cometary behavior, but never fragmented to this degree. We've witnessed cometary fragmentation countless times within our own solar system, Comet Shoemaker-Levy 9's spectacular breakup and subsequent collision with Jupiter in 1994 remains the most famous example, but those were objects native to our solar system, following predictable paths, subject to known forces. 3I Atlas brings with it the unknown variables of interstellar space, different composition, different thermal history, different structural properties forged under conditions we can only theorize about. The precision of these measurements, however, comes with caveats. We're observing these objects from Earth, across hundreds of millions of kilometers, trying to discern details that push the limits of even our most sophisticated telescopes. The brightness measurements that allow us to estimate size assume albedos that might be completely wrong. The trajectory predictions assume no further fragmentation and no non-gravitational forces, assumptions that recent observations call into question. Every number I've shared carries an uncertainty band that, while carefully calculated, represents our best educated guess rather than absolute truth. But what if these numbers hide something more? What if the velocities we're measuring, the fragmentation patterns we're observing, the proliferation of new objects we're documenting? What if they're symptoms of a process we don't understand at all? The numbers tell us what is happening, they don't yet tell us why. Every interstellar visitor carries with it the promise of revelation, a chance to sample material forged in alien stellar environments and understand how other star systems compare to our own. 3I Atlas seemed poised to deliver on that promise, presenting initially as a typical long-period comet, albeit one with an unusual trajectory originating from beyond our solar system. But as observation campaigns accumulated data, as spectroscopic analysis revealed the object's composition, as fragmentation patterns emerged, it became clear that typical is precisely what 3I Atlas is not. The first anomaly emerged from spectroscopic observations conducted at the Very Large Telescope in Chile. The light reflected from 3I Atlas, when split into its component wavelengths, revealed absorption lines corresponding to water ice, carbon dioxide, and carbon monoxide, standard cometary ices. But buried in those spectra were signatures that shouldn't be there. Complex organic molecules with structures that suggested formation temperatures far colder than the frigid outer reaches of even our most distant Kuiper Belt objects. We're talking about temperatures within a few degrees of absolute zero, conditions that exist only in the depths of interstellar space or in the coldest regions of protoplanetary disks. Dr. Michael Terrazas, a spectroscopist at Caltech, published preliminary findings that showed absorption features consistent with polycyclic aromatic hydrocarbons, PAHs, in configurations that implied minimal thermal processing. It's as if parts of this object have never been warmed, he noted in a press release. We're seeing pristine interstellar chemistry, molecular structures that have survived unchanged since their formation, potentially billions of years ago. That finding alone would be remarkable, worthy of celebration and extensive follow-up study. But it's the fragmentation behavior that transforms this chemical curiosity into something unprecedented. Standard cometary fragmentation occurs through well-understood mechanisms. Solar heating causes sublimation of ices, creating internal pressure that can crack weakened structures. Rapid rotation can induce centrifugal forces that overcome structural integrity. Tidal forces near massive bodies can tear objects apart. We've modeled these processes extensively, matched simulations to observations, refined our understanding through decades of study. The fragmentation of 3I Atlas doesn't match any of these patterns. The breakup began too far from the Sun for thermal stress to provide a complete explanation. The parent object's rotation rate, measured through periodic brightness variations, was moderate, not nearly fast enough to induce rotational breakup. And while the object passed relatively close to the Sun at perihelion, the timing of fragmentation occurred after that closest approach, when thermal stress should have been decreasing. It's as if the object waited until it was leaving the inner solar system before deciding to disintegrate. More puzzling still is the continued fragmentation. Most cometary breakups are single events. Structural failure produces fragments that then follow their separate trajectories. But observations of 3I Atlas show an ongoing process. New objects appear in the tracking data every few days, objects that weren't present in previous observations. Either we're continually improving our detection capabilities, possible but unlikely to account for the full pattern, or the fragments themselves are fragmenting, or the original object is producing daughter fragments over an extended period through some mechanism we don't understand. The velocities at which fragments are separating provide another anomaly. When a comet breaks apart passively, fragments drift away from each other at speeds determined by the structural forces at the moment of breakup, typically a few meters per second. But several fragments of 3I Atlas are receding from the main group at speeds exceeding 200 meters per second. That requires an active propulsion mechanism, some force accelerating these fragments beyond what passive breakup can explain. Outgassing can provide such acceleration, but the spectroscopic observations don't show the expected jets of gas that should accompany such vigorous cometary activity. Comparing 3I Atlas to previous interstellar visitors only deepens the mystery. Oumuamua, our first confirmed interstellar object, displayed its own anomalies, unexplained acceleration consistent with outgassing, but without visible outgassing signatures. That led to considerable debate, including exotic hypotheses about artificial origins, though the consensus eventually settled on unusual outgassing of pure hydrogen or nitrogen ices. 2I Borisov, by contrast, behaved exactly as expected for a comet, showing normal outgassing, typical fragmentation near perihelion, and chemical signatures consistent with formation around another star, but under conditions similar to our own outer solar system. 3I Atlas falls somewhere between these extremes, exhibiting both cometary behavior and inexplicable deviations. It outgasses like a comet, but fragments unlike any comet we've studied. It carries interstellar chemistry, but behaves in ways that have no precedent in our catalogue of interstellar visitors. The scientific papers emerging from observation campaigns are peppered with qualifiers: unusual, unexpected, not fully understood, requires further study. This chemical signature, this fragmentation pattern, this proliferation of secondary objects, each anomaly on its own, might be explained away as an edge case, a rare but natural phenomenon. But taken together, they sketch a portrait of an object that challenges our categorical understanding. What if what we're witnessing isn't a comet at all, at least not in the traditional sense? What if the interstellar environment produces structures, behaviors, dynamics that our solar system-centric models simply don't account for? This bears repeating. The evidence doesn't suggest anything beyond natural processes, but it does suggest that our understanding of what natural processes encompass for interstellar objects remains incomplete. The anomaly of 3I Atlas isn't that it defies physics, it's that it operates within physical regimes we've never had the opportunity to study before. And as these fragments approach Mars, as our instruments gather ever more detailed data, the anomalies multiply along with the objects themselves, opening doors to speculation, even as science works to close the gaps in our understanding. Now we must address directly and precisely what happens if the worst-case scenario unfolds. Let's dispense with speculation temporarily and focus on hard calculations, on the physics of impact, on the actual threats posed by these objects, should trajectories align in the most unfortunate ways possible. This analysis matters not because the probabilities favor disaster, they don't, but because understanding the genuine risks allows us to separate reasonable concern from unfounded panic. The most immediate concern involves our assets in Martian orbit. We currently operate 7 active spacecraft around Mars: NASA's Mars Reconnaissance Orbiter, MAVEN, Mars Odyssey, the European Space Agency's Trace Gas Orbiter, and Mars Express, the UAE's Hope Orbiter, and China's Tianwen-1 orbiter. These spacecraft, representing billions of dollars in investment and decades of accumulated scientific data, orbit Mars at various altitudes between 250 and 50,000 kilometers above the surface. Several of these orbits intersect with the projected path of the 3I Atlas debris field. Let's calculate what an impact would mean. The smallest tracked fragment at approximately 100 meters in diameter, and assuming a typical cometary density of 500 kilograms per cubic meter, has a mass of roughly 2.6 million kilograms. Moving at 34 kilometers per second, it carries kinetic energy of approximately 1.5 x 10^15 joules. That's 360 kilotons of TNT equivalent, roughly 25 times the yield of the Hiroshima bomb. A spacecraft, even one as robust as the Mars Reconnaissance Orbiter, massing roughly 2,000 kilograms, would simply cease to exist upon impact. There would be no damage assessment, no partial survival, just instantaneous conversion of spacecraft into an expanding cloud of plasma. But the probability of such a collision is vanishingly small. Space is profoundly empty. The Martian orbital space from the surface to 50,000 kilometers altitude encompasses a volume of approximately 1.6 x 10^17 cubic kilometers. Our 7 spacecraft, even accounting for their extended solar panels and antennas, occupy a combined volume of perhaps 1,000 cubic meters, 10 tau 6 cubic kilometers. The cross-sectional area matters more than volume for collision probability, but even there we're talking about a few hundred square meters of spacecraft surface versus the millions of square kilometers of space through which the debris field will transit. The JPL Near-Earth Object Studies Group, which regularly calculates impact probabilities for asteroids approaching Earth, has applied their methods to the Mars situation. Their analysis, published in an internal memo that was later made public, estimates the probability of any fragment striking any orbital asset at approximately 1 in 8,000. That's not zero, that's not negligible, but it's low enough that the precautionary measures being planned, slight orbit adjustments to move spacecraft out of the highest risk zones, are sufficient to reduce the probability to effectively zero. What about the Martian surface? Perseverance, Curiosity, InSight, now inactive but still present, and China's Zhurong rover all sit on or beneath the Martian surface. The thin atmosphere provides some protection. Fragments smaller than about 10 meters will ablate completely before reaching the ground. Larger fragments will survive atmospheric entry and impact. The smallest fragment that could threaten a surface rover, surviving atmospheric deceleration and carrying sufficient energy upon impact to cause damage across a meaningful area, would need to be at least 50 meters in diameter. The calculation of surface impact probability is straightforward but telling. Mars has a surface area of 145 million square kilometers. Each rover, including its operational sphere of influence, occupies perhaps 10 square kilometers. The probability that any given fragment impacts within that zone is 10 divided by 145 million, or roughly 1 in 14 million. With 43 tracked fragments, the cumulative probability rises to about 1 in 330,000. These are lottery odds levels of improbability. Even the worst-case scenario of the largest fragment, 3I Atlas b, at 2.1 kilometers diameter, impacting Mars, produces consequences that are scientifically fascinating but not civilization-threatening. Such an impact would deliver approximately 4 x 10^21 joules, close to 1 million megatons of TNT equivalent. The crater would be roughly 35 kilometers in diameter. The global dust cloud would temporarily alter Martian climate, but Mars has endured countless such impacts throughout its history. Our robotic explorers, if positioned in the wrong hemisphere, might lose solar power temporarily as dust blocks sunlight. They would not be destroyed by the blast itself unless they happen to be in the immediate impact zone. Again, improbable. This bears repeating. The worst-case physical scenario, the one that keeps mission planners occasionally checking their calculations at 2 a.m., involves not widespread destruction, but the loss of one or possibly two orbital spacecraft, with a probability low enough that we face far greater statistical risks every time we launch a rocket through Earth's increasingly crowded orbital space. The Martian surface assets face essentially zero risk of direct impact. Dr. Chen, in her most recent briefing, put it succinctly: "We're not dealing with a catastrophe, we're dealing with a manageable navigation hazard that requires attention and precautionary measures, but does not rise to the level of existential threat to our Mars exploration program." NASA has already calculated the propellant requirements for moving the highest-risk orbiters. The maneuvers are small, well within operational margins, and will be executed a week before closest approach. But what if the real worst case has nothing to do with physical danger? What if the trajectories all prove benign as expected? What if the fragments pass Mars harmlessly as calculations suggest they will? What if the question isn't whether these objects threaten our machinery, but whether they threaten our understanding? What if the worst case isn't impact, but revelation? That's the territory we venture into next, where speculation begins and comfortable certainties crumble. Let's venture deliberately and explicitly into speculative territory. Everything that follows in this chapter represents not confirmed science, but rather intriguing possibilities, scenarios that a subset of respected scientists consider worth examining, even as the mainstream regards them with justified skepticism. I want to be absolutely clear about this boundary we're crossing. We're leaving behind the domain of trajectory calculations and impact probabilities and entering the realm of what if, where established facts give way to provocative questions. The panspermia hypothesis, in its basic form, suggests that life did not originate independently on Earth, but arrived here via some cosmic delivery mechanism, perhaps aboard comets, asteroids, or even interstellar objects like 3I Atlas. This idea has a long and contentious history in astrobiology. Sir Fred Hoyle and Chandra Wickramasinghe championed versions of panspermia in the 1970s and 1980s, proposing that comets could harbor bacteria and viruses, seeding life throughout the cosmos. Their ideas were met with considerable resistance, primarily because the extreme conditions of space, hard vacuum, intense radiation, temperature extremes, seem incompatible with biological survival. Yet recent discoveries have softened that resistance somewhat. We've found extremophile organisms on Earth that survive conditions once thought impossible for life. Bacteria that thrive in nuclear reactor cooling pools, microorganisms extracted from Antarctic ice after millions of years, tardigrades that survive exposure to the vacuum of space. The discovery of complex organic molecules in interstellar space, in molecular clouds, in protoplanetary disks, has established that the building blocks of biochemistry are cosmically abundant. The question isn't whether organic chemistry occurs in space, it clearly does, but whether that chemistry ever crosses the threshold into biology. Enter Dr. Yuki Tanaka, an astrobiologist at the Institute for Astrobiology in Tokyo, who has published several papers exploring the possibility that interstellar objects could serve as vectors for panspermia. Her work focuses on the protected interior hypothesis, the idea that while the surface of an interstellar object experiences destructive radiation, the interior, shielded by meters or kilometers of ice and rock, could maintain conditions compatible with biological preservation. We're not talking about active, reproducing organisms, Dr. Tanaka explained in a recent interview. We're talking about spores, dormant forms, perhaps even just complex organic precursors that could, under the right conditions, seed the chemistry necessary for life to emerge. Could 3I Atlas be such a vector? The spectroscopic evidence of pristine interstellar chemistry, those complex organic molecules that have never been thermally processed, at minimum indicates that the object's interior has remained cold throughout its journey. If it originated in a protoplanetary disk around another star, If that disk harbored the same chemical evolution that led to life in our own solar system, if some mechanism preserved that chemistry through millions of years of interstellar travel, a chain of ifs that strain credulity but don't quite break it, then 3I Atlas could theoretically carry biological potential. The fragmentation event takes on new significance under this speculative framework. What if the breakup is not merely a structural failure but a delivery mechanism? Intact, 3I Atlas would pass through our solar system, perhaps shedding some material, but largely remaining a unified object continuing its journey into interstellar space. But fragmented, dispersed into dozens of smaller pieces, the object maximizes its opportunity to interact with planets, to deliver material, to scatter its contents across a wider volume of space. This is not to suggest intentionality, nature has no intentions, but rather to note that fragmentation increases the probability of material exchange with solar system bodies. Dr. Marcus Webb, a planetary scientist at Cambridge University who has studied cometary fragmentation for decades, offers a more skeptical perspective that's worth considering. The panspermia hypothesis faces a fundamental challenge: transfer probability, he notes. Even if an interstellar object carries biological material, the probability of that material surviving fragmentation, surviving atmospheric entry, surviving impact, and depositing in an environment where it could influence the development of life is astronomically small. We're multiplying tiny probabilities together and hoping for a miracle. But here's where the speculation becomes more intriguing. What if the multiplication of objects isn't random? What if there's a pattern to the fragmentation, a structure to the debris field that our current observations haven't fully characterized? Some researchers examining the preliminary trajectory data have noted that the fragments don't disperse isotropically. They don't spread equally in all directions. There's a preferential direction to their separation, a bias that could be explained by rotational dynamics or by asymmetric outgassing, but that also creates a debris field with higher density along certain vectors. Mars happens to lie along one of those higher density vectors. Is that coincidence, or is it selection bias? We notice the pattern because we're paying attention to Mars, but in reality there are higher density vectors pointing in many directions. The data set is too limited to say definitively, but the question nags at those willing to entertain unconventional possibilities. If you were designing a delivery mechanism, if you wanted to maximize the probability of material reaching planetary bodies, a fragmenting interstellar object that disperses along planetary orbital planes would be remarkably efficient. Let me be clear, there is no evidence that 3I Atlas is anything other than a natural cometary object that happens to be fragmenting in ways that challenge our models. The panspermia hypothesis, even entertained seriously, does not require or suggest anything artificial or intentional. It simply proposes that interstellar objects could be a mechanism by which organic chemistry, and perhaps even biological material, moves between star systems. The conventional view that life on Earth originated here through terrestrial chemical processes remains far more likely, supported by considerably more evidence and consistent with everything we understand about biochemistry and evolution. But if we're watching an object fragment and approach Mars, if that object carries pristine interstellar chemistry, if the possibility exists, however remote, that it could deposit material unlike anything currently present in our solar system, then the question becomes not is panspermia true, but rather, should we be prepared to look for evidence if it were? What would such evidence look like? How would we detect it? What precautions should we take as these fragments pass through Martian space? This speculation opens profound questions about cosmic connectivity, about whether the galaxy is more interconnected than our isolated perspective suggests, about whether the origins of life might be a distributed phenomenon rather than isolated events. It's speculation that demands we maintain rigor, even as we explore possibilities, that we distinguish carefully between what we observe and what we imagine, between what the evidence shows and what our hopes or fears project onto ambiguous data. Let's go deeper into the most dramatic what-if scenario, acknowledging explicitly and repeatedly that we're now firmly in the realm of speculation, exploring implications of possibilities that have no evidence supporting them, but that exercise our thinking about preparation and response. This is science fiction grounded in real physics, a thought experiment that illuminates both our capabilities and our limitations. What if 3I Atlas fragments carry not just organic chemistry, but actual biological contamination? What if the debris field approaching Mars could alter the biological baseline of another world? Imagine this: one of the larger fragments, perhaps 500 meters in diameter, impacts the Martian surface in a region near the equator. The impact is violent, releasing energy equivalent to 100 megatons of TNT, excavating a crater 3 kilometers across, throwing Martian regolith into ballistic trajectories that will rain down across thousands of square kilometers. But within the ejector, mixed with pulverized Martian rock, are fragments of the impactor itself, ice shards, dust particles, organic compounds that have survived the shock of impact, shielded by the bulk of the fragment's mass from the worst of the heat and pressure. In a conventional scenario, this material would simply become part of Mars. The organic compounds would be destroyed by solar UV radiation within hours or days. Any complex structures would degrade. The interstellar visitor would become indistinguishable from the countless previous impacts that have shaped Mars throughout its history. But in our speculative scenario, what if some of that material was different? What if protected within the fragment's interior were structures, call them spores, or resilient organic matrices, or crystalline arrangements of complex molecules that could survive the impact? The Martian environment is harsh, but not uniformly so. The surface experiences deadly radiation, temperature swings of 100 degrees Celsius between day and night, and a near-vacuum atmosphere that would be instantly fatal to any terrestrial organism. But beneath the surface, conditions moderate. At depths of just a few meters, temperature becomes stable, radiation exposure drops to manageable levels, and trace amounts of water ice exist in many regions. If impact ejector carries material underground, if fragments are buried rather than exposed, the environment becomes less immediately hostile. Here's where the speculation becomes truly challenging. What if this material, under Martian conditions, could begin some form of chemical process? Not life as we understand it. That's almost certainly too much to expect from random delivery of foreign organic chemistry. But perhaps something autocatalytic, something that promotes the assembly of complex molecules, something that alters the local chemical environment in detectable ways. Astrobiologists have speculated about shadow biospheres, alternative forms of biochemistry that might exist on Earth or elsewhere based on different molecular assemblies, different metabolic pathways, using different solvents or energy sources. If such a process initiated on Mars, triggered by the introduction of exotic organic chemistry from an interstellar source, what would we observe? The most direct signatures would be chemical, anomalous concentrations of specific organic compounds in regions near impact sites, distributions of molecules that don't match Martian background chemistry. Isotopic ratios would be telling. Material from another star system would carry different ratios of carbon-12 to carbon-13, nitrogen-14 to nitrogen-15, reflecting the different nuclear processes in different stellar environments. Our current Mars assets could, in principle, detect such anomalies. The sample analysis at Mars, SAM instrument, aboard Curiosity, can identify organic molecules at parts per billion concentrations and measure isotopic compositions with remarkable precision. The Sherlock instrument on Perseverance uses ultraviolet Raman spectroscopy to detect organic compounds and map their distribution. If fragments land anywhere near either rover's operational area, itself a remote possibility, but we're in speculative territory, we have the tools to investigate. But here's the darker edge of this speculation. What if we detect something anomalous and can't explain it through conventional Martian geology? What if the chemical signatures point unmistakably toward exotic organic chemistry, unlike anything we've catalogued? The scientific triumph of such a discovery would be shadowed by a profound question. Have we witnessed contamination? Not contamination of Mars by human activity. We're extraordinarily careful about planetary protection protocols, but contamination by cosmic delivery, by the random intersection of an interstellar object with a planet we're actively studying. The implications cascade outward. Every measurement we've taken on Mars, every conclusion we've drawn about Martian chemistry, about the potential for past or present life, about the planet's habitability, all of it becomes suspect if we can't distinguish native Martian material from recently delivered interstellar chemistry. The astrobiology community has spent decades establishing baselines characterizing what Mars is like, so that any deviation might signal biology. But what if the baseline shifts beneath our feet? What if Mars tomorrow is chemically different from Mars yesterday because an interstellar visitor scattered exotic material across its surface? Let's take this speculation to its extreme edge. What if the material delivered by 3I Atlas fragments doesn't just alter Martian chemistry, but triggers some form of propagating process? Not replication in the biological sense, but perhaps crystal growth incorporating organic molecules or autocatalytic chemical cycles that spread through Martian regolith wherever conditions permit. This is deep speculation now, straining against the boundaries of known chemistry, but it's worth examining the implications if only to understand what we should be watching for. Such a process, if it occurred, would likely be slow, glacially slow by human standards, measured in decades or centuries rather than hours or days. We wouldn't see dramatic changes in real-time observations, but we might see the beginnings, localized chemical anomalies that expand over subsequent measurement campaigns, regions where organic concentrations increase in ways that mass transfer from wind or water can't explain. The pattern would be subtle initially, perhaps dismissed as instrumental artifacts or sampling biases, but growing more pronounced as time passed. The planetary protection implications become severe under this scenario. NASA and ESA follow strict protocols to prevent contamination of Mars by terrestrial biology. We sterilize spacecraft components, we limit organic materials, we document everything that might carry Earth life to another world. But those protocols assume the threat flows one direction, from Earth to Mars. They don't account for Mars becoming contaminated by interstellar material, then becoming a reservoir that could theoretically transfer that material back to Earth through return samples. The Mars Sample Return mission, currently in planning stages, aims to bring Martian rocks back to Earth for analysis in terrestrial laboratories. Those samples would be contained in multiple nested barriers, opened only in biosafety facilities designed to prevent any hypothetical Martian biology from escaping into Earth's environment. But the protocols were designed around the assumption that Martian material is Martian, formed here in our solar system, subject to the same chemical and physical processes that govern all solar system bodies. If Mars has been contaminated by interstellar material, if those samples could carry chemistry or structures unlike anything terrestrial, the containment protocols might need reassessment. This speculation veers into territory that science fiction has explored for decades: the cosmic contamination scenario, the introduction of alien chemistry that interacts unpredictably with native environments. Michael Crichton's The Andromeda Strain imagined a crystalline extraterrestrial organism arriving via satellite and causing catastrophic consequences. That fiction was, of course, deliberately dramatic, designed for entertainment rather than plausibility. But strip away the catastrophic consequences, remove the immediate danger, and you're left with a genuine question. How do we respond to the introduction of genuinely alien chemistry into a planetary environment we're actively studying? The answer, from both scientific and practical standpoints, is carefully, methodically, and without panic. If anomalous chemistry were detected, the first step would be rigorous verification, ruling out instrumental error, contamination from spacecraft components, and misinterpretation of data. Then would come intensive observation, characterizing the anomaly precisely, mapping its extent, measuring its properties. Only after exhaustive conventional explanation had been attempted and found wanting would the extraordinary hypothesis that we're seeing consequences of interstellar material delivery be seriously entertained. And even then, even if evidence pointed toward exotic chemistry delivered by 3I Atlas fragments, the response would be scientific opportunity, not existential crisis. Mars is already a hostile environment by terrestrial standards. Any process triggered by interstellar material would be operating under Martian constraints: low pressure, low temperature, high radiation, minimal liquid water. The probability that such a process could threaten Earth, even if samples were returned, is vanishingly small. We're talking about chemistry that evolved under different stellar conditions, trying to function in an environment utterly unlike its origin. It would be scientifically fascinating, potentially revolutionary, for our understanding of cosmic chemistry and astrobiology, but not dangerous in any conventional sense. This bears repeating. This entire scenario is speculation built upon speculation, a thought experiment exploring consequences of premises that have no evidentiary support. The fragmentation of 3I Atlas is almost certainly a natural cometary process. The debris approaching Mars will almost certainly pass harmlessly. If any fragments impact, they will almost certainly deposit, nothing more exotic than the ice and rock we've analyzed from countless meteorites. The probability that we're about to witness cosmic contamination of Mars by biologically significant material is effectively zero. But the exercise of thinking through the scenario, of asking what if, and following the implications wherever they lead, serves a purpose. It illuminates our preparedness, our protocols, our ability to recognize and respond to genuine anomalies. It reminds us that the universe is larger and stranger than our experience suggests, that our categories and expectations are drawn from a sample size of one, this solar system, these planets, this history. And it underscores the fundamental truth that exploration carries with it not just the promise of discovery, but the responsibility of stewardship, of ensuring that our presence elsewhere doesn't corrupt the natural laboratories we're privileged to study. The fragmentation of 3I Atlas and its approach toward Mars occurs against a backdrop of profound questions about our place in the cosmos, questions that have preoccupied scientists and philosophers since we first looked upward and wondered whether we are alone. One of the most unsettling frameworks for thinking about these questions is known as the Great Filter Hypothesis, first articulated by economist Robin Hanson in 1996 and since then debated, refined, and worried over by everyone from cosmologists to evolutionary biologists. The Great Filter Hypothesis attempts to resolve the Fermi paradox, the apparent contradiction between the high probability of extraterrestrial life suggested by the sheer number of stars and planets in the galaxy, and the complete absence of any evidence for such life. Enrico Fermi famously asked, "Where is everybody?" The galaxy is billions of years old, contains hundreds of billions of stars, many with planets in habitable zones. If intelligent life is common, we should see evidence of it everywhere: radio signals, megastructures, colonization, or at minimum some detectable techno-signature. Yet we observe nothing. The galaxy appears silent, empty, devoid of obvious intelligence beyond our own. Hanson's insight was that perhaps there exists a filter, some tremendously difficult step in the evolution from non-living matter to spacefaring civilization, that almost no species ever passes. This filter could be behind us, perhaps the origin of life itself is so improbable that Earth is genuinely unusual. Or perhaps the evolution of complex cells or multicellular life or intelligence or technological civilization represents barriers so steep that almost no world successfully navigates them. If the filter is behind us, we can breathe easier. We've passed the hardest test, and our future might be secure. But the filter could lie ahead. Perhaps technological civilizations inevitably destroy themselves through nuclear war, environmental collapse, artificial intelligence gone wrong, or engineered pandemics. Perhaps there's something about advanced technology that carries with it inescapable self-destruction. If the filter is ahead, we're approaching the test that almost no one passes, and our existence might be far more precarious than we'd like to believe. Interstellar objects like 3I Atlas connect to these questions in subtle but important ways. If panspermia is real, if life can transfer between star systems via cometary delivery, then the origin of life might not be the filter. Life might be common, spreading through the galaxy via natural processes, seeding countless worlds. That would push the filter somewhere else along the chain of development, perhaps to the emergence of intelligence or technology. It would mean that the universe might be teeming with microbial life while remaining empty of civilizations. Alternatively, if interstellar objects serve as vectors for cosmic homogenization, for spreading not just chemistry, but potentially even biological forms across stellar distances, then perhaps the galaxy is more interconnected than we imagine. Perhaps life doesn't originate independently on each world, but represents a kind of cosmic ecology, where material exchanges between star systems create a web of relatedness spanning parsecs. Under this view, the question isn't whether we're alone, but whether we're all descendants of some ancient, widespread progenitor that has been redistributed through cosmic processes over billions of years. Dr. Sarah Walker, a theoretical physicist and astrobiologist at Arizona State University, has written extensively about these questions. She proposes that life might be better understood as a particular kind of information processing, a way that matter organizes itself to extract energy from the environment and propagate patterns through time. If that's true, then the question of life's origin becomes less about specific chemicals or structures, and more about the conditions that permit this kind of information processing to emerge. Interstellar objects carrying complex organic chemistry might lower the barrier to that emergence, providing molecular complexity that would otherwise take longer to evolve locally. But there's a darker interpretation of the Great Filter that's worth considering in the context of cosmic material exchange. What if advanced civilizations tend to experiment with biology, with creating or modifying life forms? And what if those experiments occasionally escape containment, not in the sense of malicious bioweapons, though that's possible, but simply through accident, through unforeseen consequences, through the inherent unpredictability of complex systems? If such events occur regularly as civilizations advance technologically, and if the results can somehow propagate through space, perhaps aboard fragments ejected from planets by large impacts, then the galaxy might contain a lot of biological material from failed civilizations, floating through interstellar space, occasionally intersecting with new worlds. This speculation verges on the dystopian, and I want to be clear that it has no evidentiary support whatsoever. But as a thought experiment, it suggests that interstellar objects might carry not just natural chemistry, but potentially the remnants of biological experiments from long-dead civilizations. Again, the probability is vanishingly small, but it's a scenario that expands our thinking about what contamination might mean in a cosmic context. The fragmentation behavior of 3I Atlas, its multiplication into dozens of objects, its trajectory toward Mars, none of this suggests anything artificial. Natural processes adequately explain everything we observe, even if the specific mechanisms remain uncertain, but the event does prompt us to think about what we would do if we ever did detect genuine evidence of extraterrestrial technology or biology. How would we respond? What protocols exist? Who decides? The SETI protocols, established by the International Academy of Astronautics, outline procedures for confirming and announcing the detection of extraterrestrial intelligence via radio signals. But those protocols assume detection at a distance, communication across light years, time for deliberation, and international coordination. They weren't designed for the scenario of physical material arriving in our solar system, approaching our planetary neighbors, potentially carrying information or chemistry or structures unlike anything we've encountered. NASA's Planetary Protection Office, which I mentioned earlier in the context of preventing contamination of Mars by terrestrial biology, does have protocols for dealing with extraterrestrial samples. But again, those protocols were designed around the assumption that such samples would be deliberately collected and returned by robotic missions, not delivered unexpectedly by fragmenting interstellar visitors. The gap between our existing frameworks and the scenarios we can imagine highlights how much of our planning is based on assumptions about how contact or contamination might occur. The Great Filter Hypothesis, the Fermi Paradox, the question of cosmic biology, these aren't just abstract philosophical musings. They shape how we interpret observations, how we allocate resources for research, how we think about our long-term future as a species. If the universe is empty because intelligence is rare and precious, then our survival and expansion becomes cosmically significant. We might be one of the few chances for the universe to understand itself. If the universe is empty because advanced civilizations tend to fail some future test, then understanding that test becomes our most urgent priority. Interstellar objects serve as reminders that we're not isolated, that our solar system exists within a galaxy where material, energy, and perhaps even information moves between star systems. Every such object that passes through represents a data point, a sample of conditions elsewhere, a piece of the cosmic puzzle. Whether 3I Atlas turns out to be a mundane cometary body or something more unusual, its study enriches our understanding and refines our questions about where we fit in the vast landscape of cosmic possibilities. Let's explore another speculative framework, one that shifts our perspective from thinking about interstellar objects as mere collections of matter to considering them as potential carriers of information. This isn't about artificial messages or engineered artifacts, at least not necessarily, but rather about the deeper question of whether complex structures, whether organic molecules or crystalline arrangements, or even the configuration of isotopes, can preserve and transmit information across interstellar distances and deep time. The concept comes from several converging lines of thought in theoretical physics, information theory, and astrobiology. At its core is the recognition that information is physical. It's not some abstract concept, but rather an actual property of matter, measurable in bits, subject to thermodynamic laws, capable of being stored, transmitted, and decoded. Every atom's position, every molecule's configuration, every crystal's structure represents information. Most of that information is random, meaningless noise, but occasionally information can be organized in ways that carry meaning, that preserve patterns, that tell stories about origins and history. DNA is the most familiar example of information-bearing molecules. The sequence of base pairs along the double helix encodes instructions for building proteins, regulating cellular processes, transmitting hereditary information from one generation to the next. But DNA exists within a biological context, requiring cellular machinery to read and execute its instructions. Strip away that context, leave DNA exposed to radiation and chemical degradation, and the information degrades rapidly. DNA is a poor vehicle for transmitting information across cosmic distances and timescales. But what about more robust structures? Certain minerals, particularly those with complex crystal lattices, can incorporate trace elements in patterns that remain stable for billions of years. The zircon crystals we find in ancient rocks on Earth preserve isotopic signatures and inclusion patterns that tell us about conditions when those crystals formed 4 billion years ago. They're essentially geological memories, information about past states encoded in atomic arrangements. If such structures formed in the presence of biological activity, they might preserve information about that activity, not detailed instructions or messages, but signatures, hints, clues about biochemistry that once existed. Dr. Paul Davies, a theoretical physicist at Arizona State University, has written about the possibility of what he calls a shadow biosphere. Not alternative biochemistry existing alongside terrestrial life, but rather information about alternative biochemistry preserved in geological structures. He suggests that if Earth experienced multiple origins of life, or if panspermia delivered biological material early in Earth's history, evidence might persist in ancient minerals, in unusual isotopic patterns, in molecular configurations that don't match standard terrestrial biochemistry. Could 3I Atlas be carrying such information? The pristine interstellar chemistry we've detected, those complex organic molecules that apparently have never been thermally processed, represent at minimum information about chemical conditions in another stellar system. The specific molecules present, their chirality, the handedness of their structures, their isotopic compositions, all carry information about where and how they formed. That's valuable scientific data, regardless of whether those molecules have any connection to biology. But let's speculate further. What if the object comes from a protoplanetary disk where life had emerged? Not advanced life, not civilization, just simple, perhaps microbial life, engaging in basic metabolic processes. Such life would alter its environment. It would preferentially use certain isotopes over others, creating isotopic fractionation patterns distinct from purely chemical processes. It would produce specific organic molecules, perhaps in unusually high concentrations or unusual distributions. These signatures could be preserved in ice or incorporated into mineral structures, remaining stable even as the material is ejected from that system and travels for millions of years through interstellar space. If 3I Atlas carried such signatures, if our spectroscopic observations or future analysis of fragments could detect them, we would have discovered something profound, evidence that life exists or existed elsewhere, preserved in the chemistry of an interstellar traveler. We wouldn't learn much about that life, no detailed biology, no understanding of its structure or metabolism, just the bare fact that it existed and left chemical signatures that survived a journey measured in parsecs and eons. The fragmentation of the object becomes relevant to this speculation in an interesting way. If information is encoded in the object's structure and chemistry, fragmentation multiplies the number of distinct samples we might eventually study. Each fragment potentially carries a different cross-section through the parent body, revealing different depths, different geological or chemical layers, different chapters of the object's history. From an information perspective, the fragmentation is advantageous. It gives us more pieces of the puzzle, more opportunities to decode whatever stories the object's structure might tell. There's a thought experiment in information theory called the message in a bottle problem. Imagine you find a bottle washed ashore containing a document in an unknown language using an unfamiliar alphabet. How do you determine whether it's a message, meaningful information intentionally encoded, versus random markings that happen to look structured? The answer involves looking for patterns that are unlikely to occur by chance, regularities that suggest underlying rules, redundancies that might represent error, correction, or emphasis. Applying that framework to interstellar objects, how would we distinguish chemical signatures that represent biological information from patterns that arise purely through non-biological processes? The answer lies in specificity and complexity. Life tends to produce molecules in specific configurations with particular chirality in ratios that differ from what random chemical processes generate. Life creates order, fights entropy locally even as it increases entropy globally, and leaves fingerprints in the form of organized complexity. Our current analytical tools could, in principle, detect such signatures if they're present. Mass spectrometry can measure isotopic ratios to parts per 10,000. Spectroscopy can identify molecular structures and determine chirality. If fragments from 3I Atlas could be collected, an enormous technical challenge but not impossible, laboratory analysis could search for biological signatures with exquisite precision. But here's the epistemological challenge. Even if we detected anomalous chemistry, even if patterns suggested biological influence, we might never achieve certainty. There could always be some non-biological process we haven't considered, some exotic chemistry unfamiliar to us, some consequence of interstellar conditions that mimics biological signatures. The history of science is filled with examples of apparent anomalies that eventually received conventional explanations. The famous arsenic life announcement from 2010, where researchers claimed to have found bacteria incorporating arsenic into their DNA, collapsed under scrutiny when more careful analysis showed contamination and misinterpretation of data. This bears repeating. Finding unusual chemistry is not the same as finding evidence of life. Even finding chemistry that resembles biological signatures is not definitive proof. The standards of evidence for claiming detection of extraterrestrial life are, and should be, extremely high. Extraordinary claims require extraordinary evidence, and the burden of proof lies with those making the claim. The scientific process demands rigor, skepticism, replication, and exhaustive consideration of alternative explanations. Yet the question remains philosophically profound. If information about extraterrestrial biochemistry exists, preserved in the structure of interstellar objects, and if we're developing the tools to potentially detect such information, then we're approaching a threshold moment in human history. We might be the first generation capable of answering with actual evidence rather than speculation whether life exists beyond Earth. That possibility, however remote, justifies the intense scrutiny being directed at 3I Atlas and the anticipation surrounding its continued fragmentation and approach to Mars. The multiplying objects, the anomalous behavior, the approach to a planet we're actively studying, none of it proves anything extraordinary. But it creates opportunities for observation, for measurement, for analysis that might reveal something unexpected. And in science, the unexpected is where the greatest discoveries hide. Let's engage in a rigorous thought experiment. Assume, counterfactually and purely for the sake of exploring institutional preparedness, that some version of our earlier speculation proves true. Suppose that fragments from 3I Atlas impact Mars, and suppose that subsequent analysis reveals genuine anomalies, chemical signatures that resist conventional explanation, patterns suggesting exotic biochemistry, evidence that demands we seriously consider the possibility of cosmic material exchange with biological significance. How would our institutions, our space agencies, our scientific community respond? What protocols exist, and where are the gaps in our preparedness? The first response would be verification conducted with extreme prejudice against false positives. History teaches harsh lessons about premature announcements of extraordinary discoveries. The Mars meteorite ALH 84001, announced in 1996 as potentially containing evidence of ancient Martian life, generated enormous excitement followed by decades of debate and eventual consensus that the features observed probably had non-biological explanations. The faster-than-light neutrinos announced by the Opera collaboration in 2011 turned out to result from a faulty cable connection. These examples don't reflect poorly on the scientists involved. They reflect the reality that extraordinary claims attract intense scrutiny, and rightly so. If the Curiosity or Perseverance rovers detected anomalous chemistry near a fresh impact site, mission scientists would first check for instrumental errors, calibration issues, contamination from spacecraft components. They would repeat measurements, analyze control samples, examine the data from every possible angle, looking for conventional explanations. This process could take months or years. The science teams would bring in independent experts, share data with the broader community, and subject everything to peer review before making any public claims. Parallel to verification would come information management, deciding what to communicate, when, and to whom. NASA has dealt with this challenge before, though never in quite this context. When the Viking landers conducted experiments in 1976 that initially appeared to show biological activity in Martian soil, NASA was cautious in its announcements, emphasizing uncertainty and alternative explanations. When the ALH 84001 meteorite findings were announced, the process involved advance briefing of the President and careful coordination of the message. For a confirmed detection of anomalous chemistry potentially linked to interstellar material, the communication challenge multiplies. Space agencies would need to inform government leadership. In the US, that means the President, NASA administrator, and relevant cabinet officials. Internationally, the Committee on Space Research, COSPAR, and the United Nations Office for Outer Space Affairs would be briefed. The scientific community would be informed through peer-reviewed publications and presentations at major conferences. But what about the public? The tension between transparency and avoiding panic or misinterpretation is real. Space agencies have generally erred on the side of openness, recognizing that speculation and rumors flourish in information vacuums. The likely approach would involve a carefully staged announcement. First, publication of findings in a peer-reviewed journal. Second, a press conference with multiple experts explaining the discovery, its uncertainties and its implications. Third, ongoing updates as understanding evolves. The substantive scientific response would involve mobilizing resources for intensive follow-up investigation. Mars would become an even higher priority for missions and observations. The Mars Sample Return mission, already in planning, would gain urgency and probably expanded scope. If fragments from 3I Atlas could be collected and returned to Earth, terrestrial laboratories could conduct analyses impossible with robotic instruments. Orbital assets would be redirected to image impact sites to map the distribution of any anomalous material, to search for patterns in how fragments dispersed across the surface. International coordination would be essential. Mars is explored by multiple nations: the US, Europe, China, the UAE, India, and Russia. All operate or have operated missions there. If one nation's assets detected anomalous chemistry, sharing that data with other agencies would be critical for verification and expanded analysis. The precedent here is generally good. The scientific community around Mars exploration has a history of cooperation, of sharing data, of working collaboratively despite geopolitical tensions. The planetary protection protocols would face immediate reassessment. If Mars has received material with potentially biological significance from an interstellar source, the protocols designed to prevent terrestrial contamination would need expansion. Any future human missions would require even more stringent precautions. The Mars Sample Return mission would need enhanced containment protocols, perhaps additional layers of biological isolation, certainly more extensive testing before any samples were opened in terrestrial laboratories. Political and social implications would cascade through institutions beyond the scientific community. Religious leaders would be asked to comment on the theological implications of life beyond Earth, though many religious traditions have already considered this question and found compatibility between faith and cosmic plurality. Philosophers would explore what it means for human uniqueness, for our self-conception as the universe's only intelligent observers, if life proves to be more widespread than we assumed. The probability of societal panic or disruption, contrary to science fiction tropes, would be very low. Public reaction to the discovery of exoplanets, to the detection of potentially habitable worlds, to previous claims about Mars meteorites or subsurface oceans on icy moons, has been characterized more by interest and curiosity than fear. Most people understand intuitively that the discovery of microbial life or even just complex organic chemistry on or from Mars doesn't pose a threat to Earth. The distances involved, the differences in environment, the basic biological realities all argue against any B-movie scenario of interplanetary contagion. The economic implications might be more significant. If fragments from 3I Atlas were confirmed to carry information about extraterrestrial chemistry or biology, the commercial space industry would see a surge of interest and investment. Companies developing asteroid mining technology, orbital laboratories, or planetary exploration capabilities would become more attractive to investors. The geopolitical competition around space capabilities would intensify as nations recognize the scientific and strategic value of being able to access, study, and potentially retrieve material from interstellar objects. This thought experiment, it must be emphasized, explores a scenario with effectively zero probability of occurring. The fragmentation of 3I Atlas is almost certainly a standard cometary process. Any impacts on Mars will almost certainly deposit nothing more exotic than ice and rock we've analyzed from countless meteorites. The probability that we're about to witness some revelation about cosmic biology is vanishingly small. But the exercise reveals something important about our preparedness and our institutional frameworks. We have protocols, we have procedures, we have international cooperation mechanisms that could, in principle, handle even extremely unexpected discoveries. The scientific community has thought through these scenarios not because they're likely, but because preparedness for even low probability, high impact events is part of responsible stewardship of exploration. And crucially, those frameworks are built on principles of verification, transparency, and careful evidence-based reasoning that serve us well regardless of what we discover. The approach of fragmented 3I Atlas toward Mars raises a fundamental tension that has characterized human exploration since we first ventured beyond familiar territories. How do we balance caution against curiosity, containment against investigation, the precautionary principle against the imperative to expand knowledge? This tension isn't unique to interstellar objects or even to space exploration. It manifests whenever we encounter the genuinely unknown, but it takes on particular sharpness when the unknown arrives on our doorstep, or in this case, on our neighbor's doorstep. The history of planetary protection offers instructive precedents. When the Apollo astronauts returned from the Moon, they were placed in biological isolation for 3 weeks, despite the fact that the Moon was considered highly unlikely to harbor any life. The precaution reflected recognition that our ignorance about lunar conditions was sufficiently profound that even improbable risks deserved mitigation. The protocols were eventually relaxed as we gained confidence about lunar sterility, but the initial caution was prudent given our uncertainty. Mars presents a more complex case. Unlike the Moon, Mars has conditions that could plausibly support microbial life, subsurface liquid water, protection from radiation, chemical energy sources. The possibility that Mars harbors indigenous life, perhaps in deep aquifers or protected subsurface environments, has shaped every mission's design. We sterilize spacecraft components, limit organic materials, document everything that might carry terrestrial microbes to Mars. The goal is to preserve Mars as a natural laboratory, preventing contamination that would compromise our ability to detect native Martian life. But the arrival of material from an interstellar object flips the equation. We're no longer asking how to prevent us from contaminating Mars. We're asking whether Mars might be contaminated by cosmic processes entirely beyond our control. If 3I Atlas fragments deposit material on Mars, there's nothing we can do to prevent it. The question becomes whether we should alter our exploration strategy in response, whether the possibility of contamination changes how we conduct science on Mars. One perspective, advocated by some researchers in the planetary protection community, argues for enhanced caution. If there's any possibility that interstellar material could alter Mars's chemical or biological baseline, we should document current conditions as thoroughly as possible before any impacts occur. This would mean redirecting observational resources, potentially adjusting rover mission plans to establish better baseline measurements, creating a comprehensive snapshot of Mars as it exists before the debris field arrives. Then, after the closest approach, we would have a clear reference point for detecting any changes. The alternative perspective emphasizes that Mars has been receiving interstellar material throughout its history. Every star system leaks material into the galactic medium through various mechanisms: supernova explosions, stellar winds, gravitational interactions. That material eventually intersects with other star systems, raining down on planets in a continuous, low-level cosmic exchange. 3i Atlas might be unusual in that we're observing it, but the process of interstellar material delivery is anything but unique. Mars today is already a mixture of native Martian material and countless previous cosmic contributions. One more delivery event, even if fragments do impact, doesn't fundamentally change that reality. Dr. Alberto Feiren, an astrobiologist who has written extensively about Mars' habitability, argues that Mars is already contaminated, if that's the word we want to use. Contaminated by 4 billion years of impacts, by material exchange with Earth, through meteoritic cross-seeding, by cosmic dust constantly falling from space. The idea of a pristine Mars that we must preserve from any alteration is beautiful but unrealistic. Mars is a dynamic world, shaped by ongoing processes including material exchange with the rest of the solar system and beyond. This perspective suggests that rather than trying to prevent the inevitable, we should embrace the opportunity to study a process that has shaped planetary evolution throughout cosmic history. If fragments from 3i Atlas impact Mars, and if we can observe the consequences, we gain unprecedented insight into how planets receive and integrate exogenous material. That's valuable science, potentially illuminating processes that operated during Earth's formation and might operate on exoplanets throughout the galaxy. The debate extends to information sharing and public engagement. Should observations of interstellar objects be openly shared, made available to amateur astronomers and citizen scientists, or should they be controlled through official channels to ensure careful interpretation before public dissemination? The International Astronomical Union's protocols favor openness. Discovery announcements are made publicly, coordinates and trajectory data are shared. Anyone with appropriate equipment can make observations. That openness has benefits. It democratizes science, engages public interest, and harnesses distributed observational resources. Amateur astronomers have made significant contributions to tracking 3i Atlas, providing observations that fill gaps in professional coverage. The global community of observers, coordinating through online platforms, represents a resource that didn't exist in previous decades. But openness also means accepting that speculation, interpretation, and sometimes misinterpretation will occur in public forums before scientific consensus emerges. The balance between transparency and careful messaging becomes especially important when dealing with topics that touch on existential questions about life in the universe. Space agencies have generally navigated this well, providing accurate information while being clear about uncertainties and avoiding sensationalism. But the challenge persists. How do you communicate exciting possibilities without creating false expectations? How do you maintain public interest without feeding unfounded speculation? There's an argument that the balance should tilt firmly toward curiosity, toward maximizing our investigative capabilities, toward treating every unexpected event as an opportunity to learn rather than a threat to contain. We have one planet, Mars, where we have multiple operational assets capable of studying processes in detail. If something unusual happens there, if fragments from an interstellar visitor deposit exotic material, we have a chance to observe consequences that might inform our understanding of planetary evolution throughout the galaxy. That opportunity shouldn't be squandered through excessive caution or paralysis by uncertainty. But caution has its place. We don't fully understand even terrestrial biology, don't completely know what risks might exist from exotic organic chemistry, don't have comprehensive frameworks for assessing biosafety when dealing with material that originates beyond our solar system. The precautionary principle, the idea that when facing significant uncertainty about potentially serious risks, we should err on the side of caution, has guided environmental and public health policy for decades. Applying it to planetary exploration suggests that we should maintain protective protocols, continue containment procedures for sample return, and avoid rushing into direct interaction with material that might carry unknown properties. The synthesis of these perspectives is probably the correct approach: curiosity guided by caution, investigation informed by prudence, openness combined with rigor. We observe, we measure, we analyze, but we do so carefully, with clear protocols, with transparency about methods and uncertainties, with willingness to revise conclusions as evidence evolves. We engage the public, share our findings, invite participation, but we frame our communications carefully, distinguishing between established facts and speculative possibilities. The balance between containment and curiosity isn't static, it shifts as knowledge accumulates. Early in any investigation, when uncertainty is maximal, caution should dominate. As understanding grows, as alternative explanations are tested and eliminated or confirmed, the balance can shift toward bolder investigation. The approaching fragments of 3I Atlas will test our ability to maintain that balance, to navigate between the extremes of panic and complacency, to honor both our duty to protect what we're studying and our mission to expand human knowledge into new frontiers.